Our video for section 1.3 begins with exponential functions. They've given us a description of exponential functions, not really a definition here because they don't tell me what x is. But let's see what's going on. We're going to discuss x here in just a second. They tell me that the base b can't be 1 and has to be a positive real number. So what does that mean? Why can't it be 1? Now, what we're looking for with these exponential functions is we're looking for them all to have the same general shape. And they do. So if b were 1, let's just look at that. If b were 1, I'd have 1 to the x. If I had 1 to the x, then if x were 1, this answer would be 1. If x were 2, this answer would be 1, 3, 4. Oh, everything is 1 as the base. This would be a constant function at x equal 1, and this wouldn't look like an exponential, so that's why we exclude the 1. Also says it has to be a positive real number, meaning that 0 is not included. 0 can't be a base here. 0 is neither positive nor negative, so that's how we got that disclaimer going. Cool. Okay. My exponential functions are all going to have this same general shape. They're going to look like this. And depending on what the base is, it will mean whether or not my little J hook here is really tall or kind of flattened out some. Let's look at property 1. They tell me that b of x is defined for all real numbers, and the domain, it has no restrictions on x. I can put anything in. So the domain is this negative infinity to positive infinity. And also, because this graph is never, doesn't matter what I put, what exponent I put this positive base to, it's just never going to flip over that x-axis and become a negative y value. So the range is 0 to infinity, never crossing over and never really reaching that 0. So there's the domain and range for a generalized exponential function. Let's look at that on a graph. Alright, by this time you know I love these little sliders. So as I move this slider, my J hook gets taller, and as I move it down, it flattens out, and when b is 1, it tells me it's false. So nice little demo there of what this exponential function looks like. I can notice that its domain, negative infinity to positive infinity, range, and they really just don't change. Doesn't really matter what my b is, as long as I stick within those parameters of b not being 1 and a positive real number. Let's look at property 2 and see why this might make sense for us. It tells us that whatever your base is raised to the 0 power would be 1. And let's see why that makes sense to us. If I had 2 to the third over 2 to the third, and essentially that's 8 over 8. I know what that answer is. It's 1. I've done this before. I've done it since elementary school. If I follow my exponent rules, when I divide exponents, I keep the same base and I subtract that exponent, and 3 minus 3 would be 0. And it just makes sense to us that this answer should be 1. So I'm going to go ahead and look and define these bases raised to the 0 power, as long as it's a positive real number, to be 1. Now I'm not extending that to all numbers, just positive real numbers as my base. I'm going to say that raised to the 0 power is 1. Now let's look at 3 by looking at our graph. And property 3 makes the assertion that this is an increasing function, meaning that as I walk along the x-axis from left to right, just like I read, this function is increasing, or the y values are increasing, and that is indeed true. The next assertion is that if my base is in between 0 and 1, that means that I could essentially write this as a negative exponent. That's what that means. If I did that, then this function, and notice how as b increases it flattens out, and as it decreases it gets taller. What this means is as I walk this function from left to right, this function is decreasing, or the y values are decreasing. This next little blurb is just to discuss this value of e. And this value of e is a special value if I have e as my base. It is the only place where at this x value of 0, the slope there is 1. And that's going to be important to us and later on in our course, but right now we just go, oh, okay. But I promise you eventually you'll love that property. So it is the slope of that tangent line. Alright, for inverse functions I've chosen to look at f of x equals 2x. And the inverse of that function would be x divided by 2. And if you'll notice, the domain and the range values have exactly flip-flopped, or have exactly exchanged. That is what an inverse function is. The domain is the range and the range is the domain for an inverse function. I gave you an example of a function in its inverse. I gave you 2x and x divided by 2. Not all functions have inverses. In order for a function to have an inverse, it has to be a one-to-one function. I know when we discussed the definition of function, we talked about the fact that each x corresponded to exactly one y. And this was for a function. A one-to-one function is like a monogamous function. Each x has one y and each y has one x. You'll notice this function here passes what we call a horizontal line test. This function does not pass the horizontal line test because this value of y, whatever it is corresponding to 3 different values of x. In other words, this y is really cheating on his little x's that he's got going on here. A one-to-one function is like a monogamous kind of relationship. Example, they want you to come up with sections of the graph that could pass a horizontal line test. So this is a function because it passes a vertical line test, but it definitely is not one-to-one. However, if I just looked at, say, this section from here on, and I just disregarded the rest, you could say that this function had an inverse or was one-to-one if I looked at it from 1 on up to infinity, because it would be one-to-one from there. If I looked at that function in between this section, in between 0 and 1, you could see that it would pass a horizontal line test just in this little blue area here. So I would say from 0 to 1 it would pass a horizontal line test. Likewise, the pink section from -1 all the way up to 0, just looking at my x's here, checking out my domain, and this green section here could pass a horizontal line test, that -infinity all the way up to -1. There we have it. Just to reiterate, there is a theorem talking about the existence of an inverse function, and this theorem states that f must be a one-to-one function, and if I can restrict the domain so that it is 1 to 1, which I actually do on an x squared case. In order for x squared to have an inverse, I restrict the domain and say that I am only going to talk about this section of the graph from here on. So from 0 all the way up to infinity, that's what I'm going to talk about. This y equals x squared minus 1 doesn't have an inverse over its entire domain. It just has an inverse either on this side or on this side. And that's one of the reasons why you might think about the square root of x. His domain is restricted in this realm. In our next little bit, they've given us a procedure for finding inverses. So let's try to follow their procedure. I'm going to say y equals 2x plus 6 in step 1, and then I'm going to solve it for x, and I'll get 2x equals y minus 6, x equals y minus 6 over 2. The next step is interchange the x and y equals x minus 6 over 2. And then we need to clean this up and say that the inverse of our original function x is x minus 6 over 2. Cool. Let's play it again. We'll need to restrict this domain. We're going to say that the domain is going to be restricted, and we looked at this in the previous example, from 0 to infinity. That way I can have an inverse. So y equals x squared minus 1. I'm going to solve for x. Y plus 1 equals x squared. X equals square root of y plus 1, and I need to remember my positive negative case. Swap my x's and y's. And I'm going to be looking at the positive domain, so I will just look at this particular section. Let's clean this up because of the way I've defined my domain. And there's his inverse. Next, you can see on these graphs I've plotted for you. This is the blue is the 2x plus 6, and the red is the x minus 6 over 2. And what I've done for you is I've plotted y equal x along this line. You'll notice that for inverse functions, they are reflections about this y equal x line because their x and y tables have flip-flop values. This next example is I plotted the entire x squared minus 1, but I'm only going to look at the domain from there on. So let me get rid of that, and notice that this is also a reflection about that y equal x line. I plotted with my calculator both this function and this function, and then have the graph available for you to look at and view. And I love these reflections about this y equal x line. A logarithm is an inverse function of an exponential. So if I'm reminded about logarithms and the fact that f of x equals b of x, I write the log as log base b of x. So let's look at some of the properties that go along with that. And here's my inverse relationships for those logs. On the domain and range, those two are flip-flopped to the exponential and the logarithm because they are exactly inverses of each other. Along with that, the restrictions on the domain and range that we had for exponential functions follow the logarithmic functions. Notice that since b to the 0 equals 1, it will follow, or I can write that log version similarly in the backwards form. And here is my graph of a logarithm. If you'll remember with me, our graph of an exponential function looked like that. Notice the reflection about this y equal x line as well. Now we have a word problem with our logs. Let's see what we can do with this. They want to know the time when the mass is 1 gram. Alright, so mass is 1 gram equals 1,000 e to the minus t over 850. In solving these logarithmic equations, what I'm going to do is get the e, or the base, all by itself. So I'm going to divide both sides by 1,000, getting that e all by itself, and I'll have 1 over 1,000 equals e to the minus t over 850. Next thing I'll do is I'm going to use my log properties because this t is sitting up here in this exponent and I need him out of there. So I'll take the natural log of both sides, and the left hand side looks ugly, but all it is really just a number because it's the natural log of 1,000, and I can punch that on a calculator. This next, I can use the log property of the natural log of e to the whatever power will just be negative t over 850. And at this point, I can multiply both sides by negative 850, and I'll have t equals negative 850 times whatever the natural log of 1 over 1,000 is, and I'll get that answer. And if you'll punch that on your calculator, you should get something in the neighborhood of 5,872 years, seeing as time is in years. Now, the change of base formulas used to be extremely important when we had calculators that wouldn't do logs of different bases. Now our calculators will do logs of different bases. So I can still use these formulas to, let's say in example 6, I've got 2x raised to the x plus 4 power, and I want to rewrite that so that it has e as its base, because sometimes the e makes it easier when I'm working problems. So I like that base of an e. So I'm going to use this rule, or this change of base rule, e to the x natural log of b. Alright, so let's see what I've got. I notice that my 2 is a b, and I know that this would equal e to the, my x in this case, I hate it when they kind of do this, but x is in where the x, but my x in this case is this x plus 4. So I'm going to say x plus 4 times the natural log of whatever my b is. So there's that x there, so you can see. I wish they'd use like a y or something else, it would have been a little better, but my b is 2. So making that look a little prettier, it's not really going to look much prettier. You could distribute that if you wanted to, but it doesn't make it look much better. But that's the answer to A. For the B part, let's see, I'm wanting to take log base 2 of x, and this actually has two parts. They want me to rewrite this so it has log base e, which is this part right here. So I'm going to write log base b of x is the natural log of x over the natural log of b. So let's see what we got here. Natural log, in this case my x is my x and my b is 2, so natural log of x over the natural log of 2. Oh, that's my answer. Okay, done with that one. So now let's write log base 2 of x equals, let's write down this next rule. They want me to use log base 32. So here I go. I'm going to write log, I always like to write these over so I can figure out which number goes where. So log base c of x over, and in this case my c is going to be 32, log base c of b, where c equals 32. So here we go, let's play. So it's going to be log 32, my x is my x, so of x log base 32, and my b in this case is 2, and I happen to know what log base 32 of 2 is. It happens to be 1/5. So log base 32 of x 1/5, and simplifying that is 5, log base 32 of x. And that concludes section 1.3, and I'll go take care of my pup.